Gnanam paramam dheyam. Knowledge is supreme.
So, let us continue with the discussion we had yesterday. What we have been talking about is electronic spectroscopy. When we talk about transitions, like what we did in row vibrational transitions, you are going to have fine structure because of sublevels that are there. Every electronic level is associated with vibrational and rotational sublevels. So, when a transition takes place, it is not as if it takes place from one level. When you talk about vibrational levels only, then the saving grace is that the level of origin can only be V equal to 0. That is what gives us the vibrational structure. But then when you consider the involvement of rotational levels as well, the level of origin is not necessarily J equal to 0, right. As you know, at room temperature, higher J levels are populated. In fact, one of the higher J levels has maximum population, and you know the expression for it, J max. Okay. So, all these rotational levels are going to contribute, and the selection rule, as we discussed yesterday, is delta J equal to plus minus 1 for all transitions, except for singlet sigma to singlet sigma transition. We learned today hopefully what singlet sigma is, and for singlet sigma transitions, the selection rules are delta J equal to 0 and plus minus 1, with the condition that J equal to 0 to J equal to 0, that kind of transition is not allowed. Okay. How we get these selection rules, maybe we will do it later, or I will ask you to read it up, it is not very difficult. But let us today see what kind of rotational fine structure we get. It is a little different from what we get for row vibrational transition. It is actually more complicated, more complex. So, let us see what happens when you have, but even before that, what is the energy? We said energy of an delta epsilon, energy for transition between two levels. That of course will be, if you write it in centimeter inverse, the wave number of the spectral line, that is going to be nu bar EV. Nu bar EV is the line that we talk about for transition from one electronic level to another electronic level between V equal to 0 and some V dash, right. So, what we have talked about so far is this kind of spectrum, right. This can be 0 0 dashed, 0 1 dashed, 0 2 dashed, and so on and so forth. Okay. Now, what we are trying to do is take one of these and see whether this can have multiple structure. Actually, it will have. This is the rotational fine structure. Okay. This is what we want to study, right. So, what will it be? In addition to this, there will be a term because of the rotational levels, and that is going to be delta B j into j plus 1. And what we discussed yesterday is that the reason why we write B inside delta, B inside the bracket after delta, is that rotational constants B are not usually the same, can be same, but not necessarily the same between two different electronic levels. Because as we discussed, the equilibrium bond length need not necessarily be the same in the excited state as what it is in the electronic ground state. So, if the equilibrium bond length is different, of course, you know that B is proportional to 1 by R0 square. So, B is also going to change. And what we discussed was, if the transition is such that it weakens the bond, then R0 square is going to become bigger. So, B is going to become smaller in the excited state. However, there can be a transition where the equilibrium bond length becomes shorter also, then it will be the other way. But what we do now is that we expand this and we expand this way, nu bar EV plus we can write B dashed J dashed into J dash plus 1, where dash indicates the excited state, excited electronic level, minus I can just write B into J plus 1, or maybe I will write B double dash into J double dash into J double dash plus 1. So, what I mean is this double dash indicates the level of origin, lower electronic state. J dash means the destination rotational levels, those associated with the excited electronic state. So, let us do it for 3 different cases. First, when delta J is equal to 0. For delta J equal to 0, what will it be? Nu bar will be nu bar EV plus B dashed minus B double dashed, and I can simply write your J into J plus 1, because J dashed is equal to J double dashed anyway in this case, right. Now, when delta J equal to 0, what is the range of J's? What are the possible values of J? Minus 1, then 0 is not there. This is one thing we have to remember, because if you remember, we said that J equal to 0 to J equal to transition is not allowed. Okay. So, range of J is 1, 2, 3 and so on and so forth. So, what kind of an equation is this? Yeah. So, what shape is it? Parabola, right. This is an equation of a parabola, right. Full parabola, half parabola. Half, because you cannot have negative values of J, and not only that, the parabola does not go all the way up to 0. Okay. It is conventional to draw a parabola that is turned by 90 degrees. I have no idea why it was drawn that way. Well, maybe I have an idea, we will talk about that. So, that kind of a diagram is called a Fortrat diagram. So, what we will do is, instead of trying to draw the spectrum is going to get complicated, as you will see. We will draw this what is called Fortrat diagram. To understand what kind of rotational fine structure comes in these electronic spectra. So, J is equal to 1 to, let us go up to 20, and the reason why I am writing J in the second column is that we will draw a parabola that is turned by 90 degrees. Okay. So, I want this column to be the y axis, I want the other column to be x axis. So, what will it be? Achha, what are the values of B dash and B double dash? What is the typical value of B? 8. Okay. So, let us say there is a 10% change. So, 10% change means how much? And let us say there is a decrease. So, B double dashed you are saying is 8 centimeter inverse, B dashed is 7.2, right. So, what will it be? And I am not going to plot this, I will only plot this delta Bj into J plus 1 kind of thing. So, it will be what? Minus 0.8 into J plus 1, minus 0.8 into B1 into B1 plus 1, right, J into J plus 1. And here we go. These are the values. So, see what is happening, minus 1.6, minus 4.8. So, it goes all the way up to minus 336, okay, and we are using centimeter inverse. So, if you go up to J equal to 20, then given the parameters, we see a total shift of minus 336 centimeter inverse. So, the reason why it is called fine structure is, what is the typical value for electronic transition? You told me the other day 10,000, 20,000, something like that, or even more. So, in 10,000 or 20,000 centimeter inverse, the total contribution, so that is the position of the maximum, right, and this one is 336 centimeter inverse. So, if I plot this, what do I get? I get that half parabola, this is what you get, alright. So, this is the Fortrat diagram for which one? P or Q or R, which branch is this? Do you call this P or Q or R? Q, right. Let us now see what happens for P and Q. So, for P, what is it? Delta G equal to minus 1. So, J dashed is equal to J double dashed minus 1. So, in this case, what we can do is, we can write it in terms of, I want to maintain the same range of j's, right. So, I will write it in terms of j double dash. What is the range of j double dash? 1, 2, 3, so on and so forth. J double dash cannot have a value of 0. So, what will it be? Nu bar is equal to nu bar EV plus B dash. Instead of j dash, what will I write? I will write j double dash minus 1 multiplied by j double dash minus B double dash j double dash multiplied by j double dash plus 1. Is this okay? Is this correct? So, that is going to be nu bar is nu bar EV plus, what do I do? Collect the terms in j dash square. So, it will be B dash minus B double dash multiplied by j double dash square, and what else do I have? Minus j double dash into B dash minus j double dash into B double dash. Is that right? So, minus B dash plus B double dash multiplied by j double dash. Is that correct? Correct? And well, let us do the other one as well. For delta j, so this is what it is for delta j equal to minus 1. What is it for delta j equal to plus 1? What will it be for delta j equal to plus 1? We will get a similar expression. What will be the only difference? Minus which one? Which one will be minus? Nu bar equal to nu bar EV, then here I have a minus, or do I have it here? Minus B dash minus B double dash j double dash square, then plus or minus? Plus or minus? Minus B dash plus B double dash j double dash. So, if I write them together, what will it be? I can write it generically, is not it? So, these PQ together I can write as nu bar PQ, sorry PR, and this I can write nu bar Q, that will be equal to nu bar EV plus minus B dash minus B double dash j dash square minus B dash plus B double dash into j double dash. That is easy, right? I hope we have not made any mistake in the second one, because second one I did not calculate, you did. Okay with that? So, let us plot one by one. Yes, sir. Sorry, plus minus should be for which one? So, what have I done? Where is the, which one is not correct? This or this? That is what I am asking. What should it be? This is plus and this is minus. This is also plus? No, yes, yeah, okay. So, I thought something is going wrong. So, this will be what? This will be plus j dash square, this will be plus minus. Is that right now? Now, I will get the correct parabola. So, which one is P, which one is Q? Which one is P, which one is R? Sorry, is this P or is this R? Delta j equal to minus 1, that is P, right? Let us do that first. So, maybe what I will do is I will just copy paste this. B dash minus B double dash, how much is that? Minus 0.8 multiplied by j dash square. So, this minus, what is B dash plus B double dash? 15.8, 15.2 multiplied by J dash. This is P, and what is Q? For Q, not Q, why I am saying Q again and again, for R, which sign should I change? The sign of J dash square, right. So, this becomes plus 15. Okay. So, let me just plot, then we will see. Yeah, there you are. So, this is the Fortran diagram for P branch, this is what it is for Q, and this is what it is for R. So, you see, for R we get a complete parabola, not complete, we get both sides of the parabola, it turns. So, and this point where it turns is called the band head. So, you can now imagine that if you overlay the PQR structure that we are familiar with from row vibrational transition is one branch here, one branch in the middle, one branch on the other side, right, nicely well separated. This is not nicely separated, that is the point I was trying to make, right. So, for both P and Q you see half parabola, and for R you actually see a greater portion of the parabola that it turns. So, what is the difference between P and Q? Can you read these values, or is that asking for too much? Now, we do not have to see everything together. This is P, right? See how far it has gone. Remember, we have used the same values for J 1 to 20. Okay. For that, we have gone up to minus 700. For R, we had already discussed minus 350. So, for P, what you get is you get lines that are more closer together or far apart. Naturally, far apart, right? Because the range that you get for V equal to 20 is more for than what it is for Q, and for R this is what you get, smaller range. So, tighter packing, and not only that, you do not get a monotonic increase or decrease, it turns. So, this point where it turns, this is called your band head. What is band origin? The position that would have you have got, that you would have got without any rotational fine structure. Okay. This is band origin for this discussion. And what is this? It is the band head. Band head means the higher energy up to which the band is there, right. So, so much for your rotational fine structure, and share it with you. This is something I had done for practice. The only difference is the B values, nothing else. So, I can share this with you, not an issue. Now, so that is the end of this part of our discussion.